Hello everyone, my name is Emmanuel Kumsin, and I'm here with my colleagues Emmanuel Della Kabwa, James Matengwa Baski. We are here for our final presentation on ENGI 1990B, and our project was supervised by Dr. Ashraf Ali Khan. The topic we are here to present is HVDC systems for high energy storage using St. John's NL as a case study. And our project has the following content. We'll first of all talk about the project objective. We'll compare HVAC and HVDC. We'll talk about the various topologies of HVDC. We'll go into the design of the converter of the project, and we will also talk about simulation results. Then we will conclude. Newfoundland has a lot of winds that can be harnessed into energy. And this has led to the project, the wind farm project, which is happening in Port of Agencia, which has an initial generation power of 300 megawatts. Our project seeks to develop a system which can interface between the project and the existing grid. These are project objectives. We will model a 1000 DC to 1000 DC isolated converter. We model a 1100 DC to 400 DC isolated converter. We will also combine multiples of isolated 1000 volt DC to 1000 volt DC converter to attain 11 kV DC to 11 kV DC multi-model converter. We will combine multiple models of the 11 kV DC to 11 kV DC MMCs to achieve 11 kV DC to 132 DC MMC. We will combine multiple models of 11 kV DC to 11 kV DC MMC to achieve 132 kV DC to 11 kV DC MMC. We also combine multiples of 1100 volt DC to 400 DC converter circuit to attain 11 kV DC to 400 DC MMC. So going forward, we will talk about HVDC and HVAC transmission and their various advantages and various differences between them. Where we'll take them property by property, and we'll first of all compare their voltage type. HVACs has a waveform at 50 to 60 Hz. HVDCs has a constant waveform. In terms of transmission distance, HVAC is suitable for short to moderate distances, and HVDC is suitable for long distance transmissions. And inductance compensation, HVAC requires inductance compensation, but HVDC does not require. Power transmission capacity per unit conductor size. HVAC has lower power transfer capabilities due to higher losses, while on the other hand, HVDC has high power transfer per unit size and length of conductors. Asynchronous network connectivity. With HVAC, it's not possible, but with HVDC, it's possible.
At this juncture, I will take over from my colleague Emmanuel Kumsin, and I would also elaborate on some key parameters on HVDC. My name is James Baski, and a team member for the project. Moving forward, I will talk on HVDC system composition, and on the screen, this composition is basically setup for either the HVDC station, the source station, or the receiving station. So basically, the source station would have a converter station where inputs from the various DC generators, like the renewable generators, would be received from a feeder. This feeder received would then be converted to a DC component and transmitted via DC lines. Now, during the process, you would have filters to filter out ripples in the AC quantities if need be. On the other side of the receiving end of the HVDC system, there may be a reactive power compensation capability or unit installed if need be. This system is widely used in countries like a typical example is that of Germany and Belgium, where Germany has a station, an HVDC station, and Belgium has a receiving station. So the system is designed in a way that AC DC component or AC or DC component can be transmitted in both directions. Now, in terms of HVDC topologies, I would talk about 3 or 4 of the topologies, and if time permits, I may cover the remaining topologies. Now, research has really evolved on the topic of HVDC, and as of today, there are numerous research that has been undertaken on the topic, and through the research we are privy to various topologies, of which during the project we are also preview to these topologies. The first topology is the point-to-point or the monopolar HVDC topology. Now, this topology is designed in a way that there's a source station and there's a receiving station. So, like the example of Germany and Belgium, Germany would have AC or DC or components from its renewable resources. It would then convert them to a DC component and transmit these components through its HVDC lines to Belgium. They would, on the receiving end, would receive the DC component. They then convert it to AC and utilize the resource as needed. The opposite is the back-to-back HVDC system. So in this case, each station would have the capability of converting both AC and DC and transmitting each way, whichever is required. Now, for the bipolar HVDC system, this system is designed in a way like a break and half system, where you have a system working and you have a redundancy. So in case you have to perform maintenance on the main system, you take out that system and you put in the redundancy to cater for the load. So the bipolar HVDC system has two point-to-point AVD system which are connected in parallel. Now, whenever maintenance is being carried out on the main system, the redundant system is brought into system, and the main system is the main system is taken out of service for maintenance. I mean, HVDC grade has to do with having multiple grades of HVDC system which are probably tied at a point to meet a specific load. So the next question will be why we chose these circuits, the dual active bridge circuit, for our HVDC converter design. I think the first point would have to be the crucial point in our design. So we needed to galvanically isolate the primary from the secondary side in our design, and that informed the selection of the dual active bridge circuit. Also, with the dual active bridge, we realized that when the switching and the phase shifting is properly done, we are able to, depending on the direction, move power to either directions, either from the primary or the secondary side. Also, from our research, we realized that the dual active bridge is more efficient, and in terms of the sizing, it's less bulkier with the DAB circuit. And also, I mean, once the size reduces, it directly reduces our cost. We're also looking at that aspect of it. So that is the main reasons for using the dual active bridge instead of the typical converter. Now, in terms of advantages, I would just go through the advantages real quick. So the first has to do with modularity and scalability. Of course, we are able to cascade several converters or base converters to generate the output that is required. In terms of harmonics, we have reduced harmonics for the dual active bridge, and also has some low switching losses because of the switching devices used in our design, which in this case are the IGBTs or MOSFETs that have power, that are efficient, and as compared to the thyristors and other switching devices. Of course, the dual active bridge converter is suitable for high voltage application, and that is one of the bases behind its selection for our design. So at this moment, I would introduce our coursemate Emmanuel Dela Akabwa to also take us through the remaining part of the presentation.
Hello, my name is Emmanuel Dela Akabwa, and I'm taking over from my colleague James Baski, and I'll be taking us through the circuit designs and the result of our simulations. So on our screen we have the rectifier circuit, which interfaces the supply from the wind farm to the converter, that is the dual active bridge. So what it does is that it takes 11 kV AC and then converts it to 11 kV DC, as can be seen in the output on the screen. So we come to, this is our base dual active bridge circuit. We designed and modeled a number of converters. So what we have here is the base, and with the base we have we did it from 1000 volts DC to 1000 volts DC converter. So this serves as the base that we use to do build our multi-module converter. And it can be seen that this base converter takes 1000 volts at the input and then gives out 1000 volts at the output. And then we have the dual active bridge circuit. Then it is also important that there are a number of parameters that we took into consideration, like the transformation ratio for the dual active bridge, and then the transformer that is used for the dual active bridge, and also the leakage inductors, which is shown as LX in the circuit. So this is a circuit showing an 11 kV DC to 11 kV DC DAB multi-module converter. The interesting thing about the dual active bridge circuit or the dual active bridge converter is that it enables bidirectional flow of power. And this is achieved by the phase shift that is specified between the input and then the output side. And basically, it is also worth mentioning that the dual active bridge circuit is basically, let's say, a DC circuit which has been inverted into AC and passed through a transformer, and then this transformed voltage based on the transformation ratio is also rectified to rectified to DC. So that is basically how the dual active bridge circuit is. And what informs the direction of flow of power is the phase shift between the input and then the output. So for us to get power to flow from one side to the other, we must ensure that the output and the input are phase shifted. So in our design, when we were doing our design, we used a phase shift of 30 degrees between the output and the input. And that enables us to transform power from the primary side to the secondary side. And also when we are doing the multi-module converters, when we are cascading them, what is also very important to notice that we need to ensure that there is a phase shift between the various converters that we are putting together in series, just to enable or establish that logical sequence of flow of power from one circuit to the other. So if we need to from the first converter to the next one, we need to, if let's say we have 10 converters that we are putting together, we take the 360 degrees and then we share it among them so that we can, maybe the first one will be switched on at 0, a phase shift of 0, then the next one will be switched on at a phase shift of 30 degrees, like that, the next one 60 degrees, all the way up to 270 degrees until maybe we move to the next one, then we get back to 0 again. So we need to establish that sequence when we are putting them in series so that we can enable or we can ensure that power is going to flow from one circuit to the other. So that is very important. But for the parallel side, because everything they are put together in a parallel circuit, the the phase shift or the phase shift between them is the same. So we maintain it at the 30 degrees. And also, another point that is worth mentioning is that we want to ensure that the system operates in a stable manner. Then we must ensure that we do not connect both sides in the same, like we don't have a parallel side, we don't parallel the input and parallel the output, or connect the input in series and then the output in series. One side must be in series and one side must be in parallel. And usually where we wish to attain the higher voltage, we connect that side in series so that we keep the other side constant. And after getting that, then we now keep the side that has been that we got the higher voltage, we keep that one to constant, and then connect the low voltage side also in series to achieve the higher voltage. So that is what we did to get our 11 kV DC to 11 kV DC DAB MMC. So this particular 11 kV DC to 11 kV DC multimodule converter, we created another subsystem out of it. So with this, we are able to raise the voltage level from 11 kV to 132. And this can also continue. We can continue raising this voltage, the voltage level, as long as we ensure that the phase shifts enables the sequence of flow of power from one converter to the other. As long as we ensure that that sequence is respected, we can continue to raise the voltage even higher than whatever that we did in our project. So the simulation results, as we can see, for the 1K, the base module, that's the output that we can see, that we get our 1 kV volt DC to 1 kV volt DC output, as we can see over there on the first graph. Then when we did the cascaded output, we were still able to get, we did different configurations. We did 11 kV to 11 kV, we did 11 kV to 1 kV, whereby we kept the secondary at 1 kV in the base converter. We connected the secondary side in parallel, whilst we connected the primary side in series, and we are able to get our 11 kV on the secondary side, and then maintained the primary side. We were able to get 11 kV on the primary side, and then maintained the secondary side at 1 kV. And then if you look at the second one, which is if you look at the three graphs on my right hand side, or the right hand side of the screen, the middle one, that one shows a cascaded circuit whereby we just use three just to show that we can achieve modularity just by connecting multiple modules together. So we just use three to do our simulation, three subsystems of 11 kV to 1 kV that we got in the third one. And then when we did the connection together, we are still able to maintain the primary at 11 kV, and the secondary side that we connected in series is able to give us our 3 kV DC. So the same sequence continued for us till we get our 11 kV to 11 kV, which we subsystemed and then maintained maybe one side also at 11 kV, whilst we sum up or we cascade, we keep the other part increasing to 132, and then the same way we can also keep the other side also at 11 kV, that is the primary, the secondary at 11 kV, whilst we connect the primary side in series in order to get our 132 kV. And these are all the results of the the various scenarios that we run. So in conclusion, we would say that we can use a dual active bridge, or a dual active bridge can be used to develop an HVDC system, and we can use it to achieve higher voltage handling capabilities, and also higher power handling capabilities, because as long as we continue cascading, depending on the way we do the cascading, we can end up increasing the voltage handling capability, or even increasing the power handling capabilities, so that we can develop a system whereby which can operate at 132 kV and even higher, in order to interface for an HVDC system. Then it is also very important to know that the para series configuration enables us to achieve a stable system, which it helps us to achieve a stable system for our cascaded multimodule converters. And then one very important thing is that whenever we are dealing with dual active bridge converters, we must be mindful of the phase shift, because the phase shift determines the direction of the power flow. And also we need to create a sequence such that even with the series connection, we are able to give it that logical flow, or allow it to attain that logical sequence of flow in terms of movement of current from maybe one converter to the other. We need to give it that proper sequencing, so that the converter can work effectively. Failure to specify these things very well will result in undesirable results. So it is very key to take into consideration the sequence of the phase shift. So this brings us to the end of our presentation, and we wish to express our heartfelt thanks and gratitude to our supervisor, Dr. Ashraf Ali Khan, who has been very helpful and has been very patient with us. And he really gave us a lot of direction as far as the work that we did in this project is concerned. We are very grateful to him, and we are very grateful to also Frederick, who also was very good and was very helpful to us. And we also wish to express our gratitude to the project coordinator, Dr. Mohsin Jamil, for also his very, 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 very useful feedback for our project. And all these things led to us to even do our presentation and submit our paper at the NETSEC conference, the 2023 just ended NETSEC conference. We are very grateful. We are thankful. We've learned a lot, and actually, our life has been positively impacted during the course of this project. We wish to thank everybody. Thank you. Bye.